Hello friends, welcome to video lecture on fluid mechanics. In today's session, we learn about the laminar viscous flow. Under this, we'll cover application of Navier-Stokes equation to laminar flow between parallel plates when one plate is moving and other is at rest. That is Cauchy flow. So let us start this derivation. Laminar flow between two parallel plates when one plate is moving and other at a rest. That is Cauchy flow. Okay. So in this case, this is the stationary plate and this is the moving plate. Okay. So in between this one, the flow is passing. Okay. So in this way, we can get that velocity distribution. Now, how this velocity distribution we can get at different points. Okay, this will clear to you in the coming part. Okay, so some of the assumptions are there. So see these assumptions: the fluid is incompressible, that is rho equals to constant. The flow is one dimensional, that is in x direction. So in this direction, the value for the velocity, that is u, is not becomes 0. Is not equals to 0. Okay, and the velocity along the remaining two axes, that is along the y and z axis, that is v and w respectively, equals to 0. The flow is steady, that is dabba u by dabba y equals to 0. Okay, so for the steady flow here, dabba u by dabba t equals to 0. Okay, the flow is independent of any variation in z direction. The body forces per unit mass are 0, that is fx equals to fy equals to fz equals to 0. Okay, now from continued equation we know dabba u by dabba x plus dabba v by dabba y plus dabba w by dabba z equals to 0. So as this one, the flow is one dimensional flow. Okay, this tends to 0, means here we can get the dabba u by dabba x equals to 0. Again this one, u is the function of this distance. Okay, this distance with us b. Okay, means whatever the variations occurs along the y direction. Okay, we can get that change in the velocity. So u is the function of y from Navier-Stokes equation in x direction. So this equation already was seen: u into dabba u by dabba x plus v into dabba u by dabba y plus w into dabba u by dabba z plus dabba u by dabba t equals to fx minus 1 upon rho into dabba p by dabba x plus mu by rho into dabba square u by dabba y x square plus dabba square u by dabba y square plus dabba square u by dabba z square. Now as per our assumption, this terms becomes 0. Okay, so this one, this one, this one, this one, this terms becomes 0. So this term is also become 0. Okay, only u is the function of y, so this term will remains into picture. Okay, this one. Now just see here, we can get a relation 1 upon rho into dabba p by dabba x. Just take this term towards the another side, so this term will remain towards the right side, mu divided by rho into dabba square u by dabba y square. So here we can get the dabba square u by dabba y square equals to, so in this way, here in this case rho get cancelled, we can get 1 upon mu into dabba p by dabba x. Now integrating this term, so why we are integrating here? So to get the value for the velocity distribution. Okay, so once I take the integration, so we can get here 1 upon mu into dabba p by dabba y. So when we take the integration with respect to y, so here y will comes into picture, so y plus this one constant also comes into picture, that is c1. Again if I integrate this term, so what we get here, we can get the u equals to 1 upon mu dabba p by dabba x. So integration of this one is nothing but the y square by 2 plus again integration of this one, the c1 actually comes outside of that integration sign, so y will remains. So integration of that dy is nothing but the y plus this one C2 will comes into picture, that is constant C2 will comes into picture. Okay, so once we get this value, our next target is to get the value for this C1 and C2 by putting the boundary conditions. Okay, now where this C1 and C2 are the constants of integration, boundary conditions are here. So what's about the boundary conditions available with us? So when we consider the value for this one y as 0, so when we consider the y as 0, means here the velocity nearer with the stationary plate becomes a 0. Okay, so here we can get the value for the C2 if we observe this equation. Okay, so here if I substitute the value for the y as 0 and ev as 0, we can get the corresponding value for the C2 as also 0. Okay, now if I consider the next boundary condition, that is y equals to b. So here if I consider the y equals to b, now here we can get the value for u equals to capital U. Now whatever the velocity of that moving plate, okay, possessed by that flow, is nothing but here we are considered as capital U. So here we can get the boundary condition for that u equals to capital U. Okay, now if you just observe this relation, u we have to replace by capital U. So u equals to 1 upon mu dabba p by dabba x. So what's about this y? So y should be replaced by b by 2. Okay, so y should be replaced here by b by 2, means b square by 4 will comes into picture. So 4 multiplied by this one 2 is nothing but the 8. Now just see here once again, if I apply the second boundary condition, that is y equals to b, the same equation. So here b square divided by here 4 multiplied by 2, so 8, then plus this one b1, means here b by 2 will comes to the picture, plus the constant value with us at 0. Now the value for the c1 we can get from this relation. Okay, c1 in this way we can get that value for the c1. So once we get the value for the c1 and c2, substitute these values again in equation number 1, so that we can get the value for this one u. So u is nothing but here I'll write or redirect this one, u equals to capital U by b into y plus 1 upon 2 mu into minus dabba p by dabba x into by minus y square. In this we can get that relation. The velocity distribution for the Cauchy flow depends upon the velocity of plate U and the pressure gradient, that is dabba p by dabba x. Now however, pressure gradient may be either positive or negative. If dabba p by dabba x equals to 0, then U equals to capital U by b into y. So if you observe here, if I say this term is 0, means automatically only this term will remains into picture, that is U equals to capital U by b into y, in this way. So in this way you can get that simple actual relation, that is U by capital U equals to y divided by b. A simple actually Cauchy flow. Now velocity profile for the different dabba p by dabba x, that is the pressure gradient. Okay, so here in this case when the value for the pressure gradient is very large value, then we can get that pattern in this way. So here in this case when u equals to this one capital U and when pressure gradient value is very greater than 0, then we can get this pattern in this way. Now similarly, when we just simply say just actually greater than dabba just greater than the 0, then we can get the parabolic profile in this way. Then we can get the linear profile when the value for pressure gradient is 0. Then again the value for this one dabba p by dabba x is less than 0, then we can get the pattern in this way. And when the value for dabba p by dabba x is very less than 0, then you can get the pattern in this way. Now shear stress. We know the relation for the shear stress. Tau equals to mu into du by dy. Already this one du by dy. This actually term with us. Just pick up this term from here. This term actually with us. Okay, by substituting the values of C1. Just pick up that term, okay, from that step and just substitute here into this step. Okay, so we can get the tau equals to mu into u by b plus 1 upon 2 into minus dabba p by dabba x into this term b minus 2y. So in the next step you can get the discharge. For that, consider a small element area of thickness dy having unit width. So discharge relation, we know discharge through small element, that is dq equals to u into dy multiplied by 1. Okay, so this indicates the area. Okay, so total discharge by considering the boundary condition. Okay, if I put the limit from 0 to b, then q equals to integration of dq from 0 to b. Okay, so what's about this dq? U into dy multiply by 1. So simply this term will remains. We know already the value for the u from this step. Okay, just pick up that value and substitute here and simplify this one. So if I integrate this term with respect to y, so what do we get here? Y square by 2. Just put the limit from 0 to b. The next one 1 upon 2 pi. This term will remain as it is. Integration of this one is the but the by square by 2 minus y cube by 3. Just put the limit for this term also. Okay, now just replace this one or just put the limit. We can get the simplified relation for this q in this way: u b square divided by 2b plus 1 upon 2 mu into minus dabba p by dabba x into b cube by 2 minus b cube divided by 3 in this way. Now at last we can get this relation this way: q equals to q equals to v in u into b by 2 plus 1 upon 12 mu into minus dabba p by dabba x into b cube. In this way you can get the final relation for the discharge. Thank you. Hope this derivation clear to you.